Welcome to the deep history of machine learning, decision trees. So in this video, what I'm going to do is I'm going to explain the motivation for going beyond traditional statistical techniques like linear regression into what we now call machine learning techniques. So I will describe a very traditional machine learning algorithm, sort of one of the bases of everything that's been built on since. And then I will also give a demonstration using a software called KNIME. Now this software is open source and it is free to use. It's a no-code software and it's very slick. It's very nice for creating workflows for AI projects. I learned about KNIME and I built my first machine learning project with the University of Wyoming at the University of Wyoming's AI for Wyoming Industries Computing Seminar. It was wonderful. Thank you very much. I only made the actual coding workshops because I had to work. I wish I could have been there for the rest, but thank you so much. I learned so much. Okay, so I want to give a little bit of background on classification. So with linear regression, what we end up usually doing is we have a response variable that is qualitative. In other words, we're getting a number as a result. Sometimes we're not interested in a number. Sometimes we actually want to classify things. And you can't classify things with a traditional linear regression model. So machine learning is the world of classification. An important point is that the prediction of a qualitative variable is classification as such. So let's move on to some specifics with decision trees. Now, decision trees are a very, very early machine learning technique. These things go back to the 1950s. They're fundamental computing ideas. Okay, so here is the very cool KNIME open source, no code machine learning tool. This thing is very cool. I would suggest downloading it if you're in a class with me because this thing is a nifty tool. And this is a very, very, very good way of sandboxing and exploring new data sets. So what we'll actually do is we'll start with a exploratory data analysis of the diabetes data set. So what we'll do is we will add the CSV reader and then we'll pull in the diabetes data set by right-clicking and designating it and then double-click. So notice it pulls in a preview with plenty of customization that we can add. Notice it's still yellow in the node. So this hasn't run yet. We're just seeing the preview. The data hasn't actually been loaded. Next, we'll add two additional nodes. We'll add a statistics node and a linear correlation node. And what we'll do is we'll connect the CSV reader to these nodes. Note, they're still all yellow. They're ready to go, but let's go ahead and run it. So the statistics result will actually show us some traditional statistics, the mean, the median, kurtosis, skew, the traditional stuff. Linear correlations actually show a correlation matrix, and the correlation matrix is very important for machine learning. The big deal with the correlation matrix is if two variables are too closely correlated, they're very, very likely to contain the same information. And so you have a redundancy of information. Multicollinearity is the fancy word for it. So much for exploratory data analysis. Let's move on to some machine learning. So we're going to go ahead and clear all this out and we're going to fetch the iris data set. Now this is one of the most popular data sets in the world. Don't think you found anything new in this data set, okay? You didn't. Here it is in R, okay? This is so built into the R programming language that you don't even need to pull a library. This thing is built in. This is a famous data set. Actually, this is from the UW presentation, by the way. So what we have is 150 samples of 3 different flowers, Setosa, versicolor, and virginica. And we have the length and width data for the sepals and petals. What we want to do is we want to classify these based on their petal and septal lengths and widths. So notice that there's no natural ranking of the 3 different types of flower. That's why we don't use a linear regression here, because we don't have a numerical way of designating the 3 flowers because they're not ordinal, they're not ranked. Using the iris data set, what we'll do is we'll go to Manipulation, Row, Transform, and we'll grab the table partitioner. We'll drag the table partition over and we'll click on F6 or right click on it, and we'll see that we're holding back 70% of the data. That means of the 150 that we have, we're going to be holding back 45 observations. Those 45 observations will come up later on. So from views, let's go ahead and grab a scatter plot and connect it to see what's happening. What we want to compare first of all is septal length to petal length. And we can see here that there are two different populations. This is what motivates classification problems, is we can see that there's two populations and we want to classify whether or not something fits in one or the other based on the characteristics. Now we get to do a decision tree. So what we'll do is we'll click on Analytics, then Mining, then Decision Tree, and pull the Decision Tree Learner over and connect it to the partitioner. We'll be using the Gini index, and we need to make sure the class column is one of the varieties of flower. The Gini index, by the way, is a famous predictor of inequality, which is a term that sure comes up a lot in AI. Next, we bring the neighboring Decision Tree Predictor, connecting the Decision Tree Learner on the top and then the held out partition on the bottom. This is an actual machine learning workflow. Finally, we add a score, and then we make sure everything runs, and we can see everything is ran when we see green lights all the way through. For the bottom line, we have a look at the confusion matrix. Remember, we had 45 that we held out. The results might be different when I'm doing the example, but when I was taking my notes, there were 18 setosas correctly identified, 10 versicolors correctly identified, but 2 of the 17 virginicas were mislabeled. This is where we're going. We have a system that has identified the 45, almost all of them correctly, and we got to those 43 of 45 correct predictions by setting up a decision tree, a classification tree that allowed us to classify new observations based on observed characteristics.